Thank you very much indeed, and good afternoon, and thank you for the opportunity to speak at your great conference. The question that I'd like to ask the audience and the panel is whether spiking could or should play any role in embodied intelligence. And I don't expect this question to be settled right away, because I don't even think it's settled in neuroscience. But this is a question that has occupied me in the last 10 years or so, and I'd like to share at least the perspective of a control theorist on that question. So as a control, something that is very clear in control nowadays is that you have this big gap between what we would call control systems on the one hand and automata on the other hand, or control and automation. So we design control systems to make systems adaptive to their environment, and we design automata to make reliable decision-making. And very often, one is at the expense of the other. So when we design adaptive systems, they are not that reliable. And when we design reliable systems, they are not that adaptive. And I think it's a big question in AI today to see how we could combine these two properties. And the question then is, if we look at the animal world, is whether spiking is something that could be qualified as both adaptive and reliable. Because spiking communication is event-based communication, and you could say that the timing of events is very analog, whereas the events themselves can be counted and reliably counted. So this is sort of a broad question. And thinking about this conference, I don't know much about embodied intelligence, and to be fair, but I thought that probably there is a lot of analogy when you think about embodied intelligence today, and you also see this sort of gap between conventional robotics and recent trends in robotics where, computation like machine learning, for instance, is emphasized. And somehow, I think in many of the examples that we have seen today, we see, again, this gap between the physics of robotics and the computation of automata. And likewise, in neuromorphic engineering, you see very much this gap between analog circuits that are sort of traditional and that were forgotten for many years, because CMOS technology was so powerful, and you see nowadays a lot of interest to sort of go back to the advantages of analog and to try to think of mixed architecture that somehow, again, exploit the mixed nature of spiking. So what I'd like to do in the next 5 minutes or so is just two things. One is to give you what I would consider the simplest illustration of properties that you can start exploiting in artificial systems once you use spiking, and then properties that you see in the animal world that you can sort of hope to transfer to the artificial world. I'll give you just one example, and then I'll spend a few minutes explaining you how we try to develop this control theory for spiking systems, and whether we have to start from scratch again or whether we can sort of leverage the existing theory. So this is just one example, but I think it's a very, very cool experiment that is not recent, that was done in neuroscience in the 90s, in fact, reproduced from an earlier experiment in the 70s, to illustrate that spiking can be both variable and yet reliable. And what you see here on the left is 10 experiments with the same neuron. And the result of those 10 experiments are superposed. And the experiment is very simple. You apply a constant current to the neuron, and the neuron starts spiking. And what you see, and this is a raster plot of the timings of the spikes over the 10 successive experiments. And what you see is that when you apply this constant current, the very first slides are somewhat aligned, but very rapidly they sort of drift apart. And that illustrates the variability of this analog system. And what you see on the right is the same neuron, again, a set of 10 experiments repeated 10 times. But this time the applied current is different in the sense that it's much more jerky. And this time you see that the spikes superpose on each other very, very reliably. And that's even more prominent in the raster plot. And so what you see on the left is sort of the analog behavior of a neuron, that if you apply a constant current, what you see, the sequence of spike is just a sort of a limit cycle. And this limit cycle, you know, is very dependent on the environment, on temperature, on stochastic variations. And on contrast, what you see on the right, each spike is a result of a threshold. Each spike is an event. And in that case, the behavior becomes extremely reliable in spite of the variability. And recently, we reproduced that exact same experiments in a neuromorphic electronic circuit. And so exactly the same result. So that I think that what we see in neuromorphic engineering is exactly the same issue. And one big issue today in neuromorphic engineering is how to fight the variability of transistors. And that's called the so-called transistor mismatch issue. And you have a lot of research and a lot of PhD dissertations devoted to calibration of those circuits. But it seems that the problem is somewhat intractable, that you cannot really fight against the variability of those analog devices. And certainly in nature, we see that nature seems to go very well with that variability. And perhaps this is a sort of a fundamental reason for spiking in nature. Of course, this is just one very simple illustration. We could describe many more illustrations at a sort of the ensemble level. How can you make advantage of rates? How can you make advantage of synchronization? How can you make, and there are lots of results that have been understood in neuroscience in the last 40 years that wait to be transferred to machines, but I think would rely a spiking architecture. So in the last 2 minutes, I'd just like to sort of flash the sort of approach that we are taking to, in the hope of leveraging the existing control theory, rather than starting a theory from scratch. And of course, if you look at conventional control theory, it looks very, very different from spiking, because you try to maintain systems at equilibrium, and instead of having this event-based communication. But what you see here is the block diagram of a sort of a very conventional control system, where that perhaps you have all had in your control class, where you have the plant, and then you control the plant with a controller. And this is here representing an arbitrary electrical neural network. So submitted some input currents, and you measure some voltage. And it could be, you know, a vector current and a vector voltage. So this could be a very naive representation of a 10,000 neural network. And what I would call the plant is sort of the passive membrane substrate. And you could make a parallel with a mechanical network. And what you see in the controller is the set of all these active devices that we call conductances. And there are two categories of them. Most of them are sort of positive conductance, and a few of them are negative conductance devices. And if we remove the negative conductance device, we have the most conventional control system. And we know we have the theory of how to design such systems, and we can. This theory nowadays is very scalable and so on. And our claim is that by just adding this red block, these few negative conductance, you can transform this very passive behavior into a spiking behavior, and control and design these thresholds to enable the properties of spiking architecture. So the research that we are pursuing at the moment is really to try to take all the classical results of control theory, adaptive control, internal model principles, and so those basic results of control theory that look old-fashioned and classical, and to transpose them to a spiking world by exploiting somehow the fact that the architecture of spiking systems is, in fact, if you look at the physical level, at the biophysical level, very close to the conventional architecture of our control systems. And if you want to know more about this, we have a recent preprint on arXiv that sort of gives the details about this, and that will be the end of my presentation. Thank you.
Thank you very much for that presentation. That was a very nice and contrasting view to those we've had from the rest of the panelists. So while we just invite back the rest of the remaining of our speakers for this panel discussion for hopefully the next 20 minutes or so, I just wonder, Rodolphe, if you have any perhaps example of where you think we could test this principle in a robotic system, or is there this mechanical approach you considered? I think transistors you mentioned is one area that we could make a direct improvement. Is there a mechanical alternative or something that you think would be an interesting first test of this approach?
Yeah, I think that we see more and more examples of actuators and sensors that rely on event-based signaling as opposed to conventional analog or digital signaling. Of course, one very famous recent examples are the event-based cameras. But also in the actuation world, we see, I think we had one example earlier today where we heard about these bistable soft valves. So that would be one example of implementing spiking actuation. And even if we think more conventionally, if you think the way we control a motor with a PWM technique, you could, in a certain way, think of this as a also event-based control. So I think that it's sort of, the answer is clearly yes. We think about recent actuators, but it's also true in a sense if you look at more conventional actuators and sensors.